For most of human history, the sky we could study ended at the range of our eyes. Galileo's first telescope moved that boundary. Hubble moved it again. In January 2022, a new one opened its mirror at a gravitational parking spot 1.5 million kilometers from Earth and moved it once more, this time, into infrared. The James Webb Space Telescope launched on the 25th of December, 2021, on an Ariane 5 rocket from Kourou in French Guiana. 3 days into the journey, its sunshield unfurled. 2 weeks later, its 18 mirror segments folded into place. On the 24th of January, 2022, it arrived at its destination, a solar orbit near the Sun, Earth L2 Lagrange point, about 1.5 million kilometers or 930,000 miles from Earth. Its primary mirror is 6.5 meters across, 21 feet 4 inches, composed of 18 hexagonal beryllium segments, each one coated with a 100-nanometre-thick layer of gold. Gold is the coating because gold reflects infrared light more efficiently than any other practical metal. Behind the mirror, a 5-layered sunshield, the size of a tennis court, keeps the telescope below 50 Kelvin, minus 223 degrees Celsius, cold enough that the telescope's own heat does not drown out the signal it exists to detect. Webb sits at L2 because L2 is quiet. L2 marks a point of gravitational balance between the Sun and Earth, where a small spacecraft holds station with minimal fuel, on the far side of Earth from the Sun, with both Sun and Earth always in the same direction. The sunshield points permanently toward them. Everything behind the shield stays cold and dark. The telescope completes one loose orbit around L2 every 6 months or so, using small station-keeping maneuvers to stay in the stable zone. The reason the coldness matters, and the reason Webb is an infrared telescope rather than a larger visible light one, comes down to the expansion of space. Space itself is expanding, and expanding space stretches the light traveling through it. The further away a galaxy sits, the more its light shifts by the time it reaches us. From ultraviolet into visible, from visible into the infrared, and for the oldest galaxies into the mid-infrared. The earliest galaxies, the ones that formed when the universe was less than 1 billion years old, emit light that no human eye can see and no visible light telescope like Hubble can fully collect. That light, by the time it reaches us, lies in the infrared. Webb's 4 instruments, NIRCam, NIRSpec, MIRI, and the Fine Guidance Sensor, together cover a spectral range from about 0.6 to 28 micrometers, most of it well beyond human vision. On the 11th of July, 2022, the first full-resolution image from the telescope appeared at a White House event, and NASA released it publicly the following day. The image centers on a galaxy cluster in the constellation Volans called SMACS 723. Light from the cluster itself is 4.6 billion years old. But the real subject of the image is the galaxies behind the cluster, whose light the cluster's gravitational field has bent and magnified around it. Some of those galaxies are 13 billion years old. We are seeing them as they were when the universe was less than 1 billion years old. NASA described the image as the deepest and sharpest infrared view of the distant universe, released to that date. The telescope's second major result came from a much smaller object. WASP-39b is a hot gas giant, roughly the mass of Saturn, closer to its star than Mercury is to ours, orbiting a sun-like star about 700 light-years from Earth. On the 10th of July, 2022, Webb's near-infrared spectrograph recorded a transmission spectrum of the planet as it crossed the face of its star. The fraction of the star's light that passed through the planet's thin atmosphere carried the chemical fingerprints of what the atmosphere contains. The 2022 analysis, published across 5 papers in Nature by the Transiting Exoplanet Community Team, detected sodium, water, carbon monoxide, and carbon dioxide. The detection of carbon dioxide was the first unambiguous identification of that molecule in the atmosphere of a planet around another star. For context, Webb can do this because the instruments sit in that quiet, cold shadow, collecting a signal that on any warmer telescope would be indistinguishable from the telescope's own thermal glow. The telescope's senior project scientist, John Mather, had spent 27 years waiting for it to start working. Mather shared the 2006 Nobel Prize in Physics for his part in measuring the cosmic microwave background, the earliest light in the universe, with the Kobe satellite, which returned its decisive anisotropy measurement in 1992. The Nobel Committee called Kobe the starting point of precision cosmology. When NASA appointed Mather JWST Senior Project Scientist in 1995, Webb had no mirror, no sunshield, and no launch date. He kept the position until 2023, when Jane Rigby succeeded him. What Webb has shown us in 3 years of science operations includes galaxies earlier and more massive than any previous model predicted, and the chemistry of atmospheres on worlds we cannot see directly. NASA expects the instrument to operate for at least another decade. Everything it shows us during that time will be a view that, before 2022, was not available to anyone. The James Webb Space Telescope is a single instrument, stationed on the anti-sun side of Earth, returning a signal in a spectrum human eyes cannot see. What it shows us was already there before it arrived. We are only now receiving it.